Hey everybody, it's Thursday, November 5th, and as you can see here in the aim today, today's video is going to be about how we can use Newton's laws to solve statics problems, which are a very specific kind of forces problem. However, before we do that, I want to take a couple minutes just to address the problem we posed at the end of the video yesterday. So at the end of the video yesterday, we showed what happens to a scale when a person is standing on that scale inside of an elevator and that elevator is moving. And so what I asked you to do after we looked at that video is I asked you, based on the information given in the video, what can you say about the motion of the elevator? And what I wrote there underneath was be sure to follow the format for elevator problem explanations in your answer. So let's just go ahead and take a quick look at that video again, just so we're all reminded about what happened. So as you can see in the video here, we have the person standing on the scale, and the original scale reading before the elevator starts moving is about 200, and when the elevator starts to move, the scale reading is about 215-ish pounds. And so this first part is just establishing the facts. You don't actually have to write this in your explanation, but I wrote here is before the elevator moves, the weight of the person is around 200 pounds. When the elevator moves, scale reading is about 215 pounds. And so the answer here requires you to, as we said yesterday, talk about the direction of the acceleration, talk about the direction of the net force, and compare the size of the forces. So an explanation should look something like this. When the elevator accelerates, the normal force is larger than the weight of the person. That's because this 215-pound scale reading is the normal force, whereas the scale reading before the elevator started accelerating was the person's actual weight. So what I wrote here is since the upward force, which is the normal force, is larger than the downward force, the weight, the net force acting on the person is upward. And since the net force is directly proportional to the acceleration, since the net force is up, the acceleration is up. That's the idea. So in this explanation, notice we've covered all of the required elements for an elevator problem explanation. You compare the size of the forces, you use that comparison of the size of the forces to talk about the direction of the net force, and then you use the direction of the net force to talk about the acceleration. I want to be very clear about one thing, though, before we wrap this up. Notice the order in which I gave those requirements, comparison of the forces, direction of F net, talk about the acceleration, is actually the exact opposite of the order I gave when I first started talking about this. Because when I just first started talking about this two seconds ago in the beginning of this video, I said you got to talk about the acceleration, you got to talk about the net force, you got to compare the size of the forces. It ultimately depends on what you're given, is the key idea in terms of how to word your explanation. So if you look yesterday, when we looked at an example of a problem here, they gave us the direction of the acceleration. So in our explanation, we said, well, the elevator is accelerating down. If it's accelerating down, the net force is down. And if the net force is down, the downward force, the weight, has to be bigger than the upward force, the normal force. But of course here, because the information that you were given was about the size of the forces, you basically do the explanation in the opposite direction. That's really all they could tell you, right? They could tell you the acceleration direction, or they could tell you the scale readings. And so which order you address these things in the explanation is dependent on how the question presents the information. And that's an important thing to keep in mind going forward. Okay, and so with that, now we are officially finished with the elevator problem, and we now are ready to address statics problems. So the first thing that we should probably do here, we should go ahead and define what statics is. And statics is a branch of mechanics, which is really what we've been doing the whole time. Kinematics, and dynamics fall into the broad category of mechanics. So statics is the branch of mechanics concerned with bodies at rest and forces in equilibrium. Now, technically, if forces are in equilibrium and the object is at rest, that's describing a situation in which the acceleration is zero. Constant velocity also would technically fall under that rubric, but statics really specifically refers to things that are not moving. And so here we're going to be focused on objects that are not moving and forces that are in equilibrium. Of course, since equilibrium conditions are like a huge part of this particular topic, we want to make sure we're being very clear about what that means. Equilibrium is a condition in which the vector sum of all of the forces acting on the object is zero. To put it very simply, they cancel out. And this means that the acceleration of the object is going to be zero. So whenever an object in these problems is going to be not moving, thus not accelerating, what that tells us is that the vector sum of all the forces, or in other words, the net force, is equal to zero. And so this means that the acceleration of the object is zero. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so the fact that all of these forces add up to zero is pretty nice, because the fact that all these forces add up to zero means that the actual physics involved in these problems is pretty straightforward, because the main equation for these problems is usually F equals ma, or the sum of the forces equals ma, but here the sum of the forces is just going to be equal to zero. And that's pretty nice, because the physics here is very clear and straightforward. But of course, whenever there is good, there is bad. What's kind of whack about these problems is that that's really the only physics you'll be doing. The rest of it is basically just trig. Now, if you can take any solace in this fact that some of these problems are basically just trig problems, at least you don't have to take an entire course called statics, as I did in college, because it really is that boring, because basically that's what you write first for every single problem. The sum of the forces equals zero, and then the rest of it is just a page of trigonometry for every single problem that you'd have to solve. Now, the problems that we're going to be solving in this course are pretty straightforward, but nonetheless, this is going to be the starting point. And something that we should be like really super clear about here is that what this means, that the sum of the forces is equal to zero, is that that's true in every single direction. So the sum of the forces in the x direction is going to be zero, and the sum of the forces in the y direction will be zero. And that's something to keep in mind as we go through these, because you're going to be applying that fact consistently. Of course, since F equals ma, that means the acceleration in the x direction will be 0 meters per second squared, and the acceleration in the y direction will be 0 meters per second squared. And of course, because for any vector, acceleration is included, you don't need to write this down because I'm sure you already realize this, but when you have two components of something to find the total, you do the Pythagorean sum. And so that means when we sort of join these facts together here, it means the overall acceleration is 0 meters per second squared. And so here is the key idea. The sum of the forces is 0, the acceleration is 0, and it means that in each direction separately, that will also be true. This is actually really super important. So take a second to pause this video here and write that down. And when you hit play, we'll start to get a sense of what these problems look like. Okay, so before we talk about how to solve these problems, I just very quickly want to take a second to show you one of these problems. So this is what one of these problems are going to look like. You're going to have something, usually hanging by strings, just sitting there. And because these problems are always going to look the same, what we're going to do is we're going to follow a very simple and straightforward procedure when we're solving these problems. So I'd like you to write this down under the heading statics problems. This is what you're going to do to solve these problems. First, we're going to draw a free body diagram. That's not included in this list, but of course, we're going to draw a free body diagram. Then you're going to write the equations from the free body diagram. And this is what we're going to do. In the x direction, we'll just take all rightward forces, because we usually call right positive, and then we'll subtract all leftward forces and set them equal to ma. Of course, that's going to be 0, though. In the y direction, we're going to take all the upward forces minus all the downward forces, and we're going to set those equal to ma. Then we're going to have a sum of the forces equation in the x direction and a sum of the forces equation in the y direction. And those two, because they're independent, need to essentially be solved as a system of equations. And so first, we'll say since the x direction equations are simpler, we'll use the x direction to solve for one tension in terms of the other. And we'll plug those into the y direction equations. And then the y direction equation will be used with the result plugged in from the x equation to solve for one of the tensions. Now, just to explain, why a reasonable question here to ask is, why is the x direction equation simpler? The x direction equation is simpler because it just involves tensions. It doesn't involve the weight of the object, right? The force of gravity is just a vertical force. And so because it's just vertical and not horizontal, the x direction equation doesn't include the weight of the object, but the y direction equation does. And so because the x direction equation doesn't involve the weight, it's going to be really easy for us to just solve that for one of the tensions in terms of the other. And then we will go ahead and plug that into our y equation, and then we can solve it. So essentially what we're doing here is we're solving this system of equations by substitution. This is a lot. So take a second to pause this video here and write this down. And when you hit play, we'll go ahead and take a good look at that problem. Before we go on to the problem, I know I just said we were going to look at it, but there's one thing I want to address very quickly. Notice the word tension is scattered throughout this description here on the slide. I want to call everybody's attention to the fact that in the picture of the problem I showed you, there were ropes. And that's why we're talking about tension. So to be clear, tension, I'm sure you already know this, and I'm sure you talk about it in shop to some degree, but tension is the magnitude of the force acting along a rope. So whenever there are ropes or strings involved, we're going to be talking about the tension in that rope. And because tension is a force, we are going to label it as an F, because it's a force, but with a subscript T. And we're basically going to be saying the force of tension, although we'll mostly just refer to it as the tension. And something that's very, very important for you to know about tension is that the tension in a rope is constant at all points in the rope if that rope is considered to be massless. Now, no ropes are actually massless, but we assume this for ropes where the mass is pretty small. And if the mass is pretty small, especially in comparison to the mass of the object, then we can consider the rope to be massless. The point here is, and you can realize this if you just take a minute to think about it, I think. If you have an object that's hanging from a rope, then it makes sense that the tension here is going to be different at all the points in the rope if the rope is heavy. Because at any point in the rope, the upward forces need to be canceling out the downward forces because this thing is just hanging there and the net force is 0. And so it should be pretty clear that up here, for example, because so much of the rope is hanging below that point, all of that rope's mass would have to be supported by this upper section of the rope here. And so the tension there would be larger. But if the mass of the rope that's down here is like way smaller than the actual mass of the object, then it's basically insignificant. And because it's basically insignificant, then we just neglect it. So this is kind of like a neglect air resistance idea. It doesn't actually not exist, but we're just going to say it's basically equal to 0. It's also true for a rope that's directed horizontally. Let's just assume I drew that straight. In reality, what actually happens is that the mass of the rope would cause this thing to sag a bit in the middle. And that is going to create all sorts of wacky tension forces directed at weird angles in the rope. And so because that situation gets insanely complicated, we're just going to go ahead and assume that these ropes are massless. There is no sagging in the rope, and that these things are just going to sit purely horizontally because they're essentially massless. And again, we can get away with that if the masses of the ropes are considerably smaller than the masses of the objects, and that's always going to be the case. Like when we do labs with ropes in this course, which I'm going to videotape and show you some of them, you will see that we use this like really super thin string. And so when we're talking about the mass of like a cart rolling on a track that's like a kilogram, the mass of that string is not going to be anywhere close to that. And by making an assumption that the rope is massless, it turns out we actually get like really super close to the actual experimentally determined result. So like if we use these assumptions to predict by calculating what like an acceleration would be, and then we measure it, they're basically the same number. It's well within the range of experimental error. If you haven't already written this down, take a second to pause this video here and write that down. And when you hit play, we'll actually go ahead and solve that problem now. So here is the problem. The problem says a 150 Newton bird feeder is supported by 3 cables as shown in figure P4.19. Find the tension in each cable. And so just because we need to be super precise about these things, we're going to call this cable, cable 1, just so we can keep track of everything. We're going to call this cable, cable 2. And notice these are joined here. And then there's actually another cable or rope, whatever you want to call it, acting below that point or existing below that point. And so we'll call that cable 3. I actually want you to draw that in your notes because this diagram, as it turns out, is going to be really important for a number of reasons. Okay, so the first and most important thing to realize here is that we have to do a little bit of thinking about this diagram. Because usually, when we draw these component diagrams, the angle that we deal with is the angle as measured from the horizontal. And so that would be these 2 angles shown here. And I would imagine, based on the way the diagram is drawn, some of you already see it. But an important thing to realize is that even though these angles are not like the specific angles you want to use, if you notice in these static problems where we have this hanging mass, we have some serious alternate interior action going on. And so that means this angle of 60 degrees is actually this angle, and that's the angle we want. So the angle, which because this is rope 2, we'll call theta 2, is actually 60 degrees. And notice that that also holds over here. This angle is 30 degrees because we have another alternate interior. And so those are the angles we want. Those are the angles we need. We're good. Okay, so the first thing I want to do here is just write down the list of knowns. So we have here that the bird feeder is 150 newtons in weight, right? The bird feeder weighs 150 newtons. So we'll put that down in our list. We know that the angle theta 1, as I just discussed, is 30 degrees. And we know that the angle theta 2 is 60 degrees. And we are looking for FT1, the force of tension in cable 1, the force of tension in cable 2, and the force of tension in cable 3. And as we mentioned, I did not write it down in the list of problem-solving steps, but as we mentioned, the first thing you want to do here is sketch a diagram, a free body diagram for this situation. And it's important to remember that ropes pull back against any force that is applied to them, right? So basically, if the bird feeder is pulling this thing down, that means the ropes are going to pull up. So tension 1 acts over here at an angle of 30 degrees. Tension 2 pulls up here, and I should label this FT1. Tension 2, FT2, acts over here at an angle of 60 degrees. And then we have down here a complicated situation. Well, essentially what we have is we have the weight of the object pulling down and the tension pulling up. And so the way that we can show this here is we can show FG pulling down, and then we can draw another little diagram here, which I think is going to make everything obvious, which is that at the point where the object is connected, you have the tension in that third rope pulling up, and we have the weight of the bird feeder pulling down. And I hope everybody realizes the first thing that we're going to do now based on these diagrams. The first thing we're going to do now based on these diagrams, and I'm going to write it here, is recognizing what's going on right here. Nothing is moving. So the first thing we're going to recognize is that the tension in cable 3 is equal to the weight of the bird feeder. And so we can write that down here like this. FT3 is equal to FG. And so that means we've already knocked out one of our two unknowns, which is that FT3 is equal to 150 newtons. And that's really all you have to do for the third tension. Now, what we have to do now to do anything else, we have to make some more progress, and we have nothing left to do except to follow that first step in the list of procedures. We're going to write our equations for the x and y direction. So we'll have the sum of the forces in the x direction equal to 0 as our starting point. And as I mentioned in that list, I just want to go back to it here. In the x direction, we take all of the rightward forces minus all of the leftward forces and set them equal to ma. And something that I mentioned the other day, which may be helpful to realize here, is that while an official free body diagram, what I've drawn over here, never actually includes components, sometimes it's really helpful to draw diagrams showing components off to the side. I always, in these component diagrams, draw the components with dotted lines. And so what you see here is that for FT1, it's going to have a horizontal component going like this, which I'll call FT1x. And ft2 is going to have a horizontal component that goes like this to the left. ft1 is going to have a vertical component that comes up, so I'll call that ft1y. And ft2 is also going to have a vertical component that goes up, and I'll call that ft2y. And those are going to be canceled out by the full weight, and notice that's not a component, so that's why I'm not drawing that dotted. So if you didn't already realize it, this diagram should make it clear that the sum of the forces in the x direction equation is going to be ft1x, the x component of ft1, the rightward forces, minus the leftward forces, ft2x, and we're going to set that equal to ma here, which is 0. And there's really not a whole lot that we can do with that, right? What we can do with that is we can say, well, that means ft1x is going to be equal to ft2x. And that's our big result from the x direction. And this is what I meant by it'll be easy to solve for one in terms of the other, because those are the only two things in that equation. Now, for the y component, it's a little bit of a different story, but still quite similar. As we said in the list of steps, you take all of the upward forces in the y direction, so that would be ft1y plus ft2y, and we set them equal, or sorry, excuse me, we subtract the downward forces, which is fg, and we set that equal to 0. And so, of course, we could go ahead and set that equal to fg, right? We could add fg to the other side and put the fg on the other side, but it really doesn't matter. And so what we should do here for now is we could just leave that. We're going to have to come back to that later. Here's the point where now you have to start to do some math. Because notice all of these equations are written in terms of the components. But we know equations that relate vector components to the full vector. And so that's what we're going to do next. So in our x direction equation, and I'm going to pop back there just to show it to you again. In our x direction equation, we have that ft1x equals ft2x. So we have ft1x equals ft2x. But we know, and I'm going to erase this, I'm just going to put it over here to reference, we know that the x component of any vector is equal to that vector times the cosine of the angle. So what I can say here is that ft1x is ft1 times the cosine of the angle theta 1. And what I can say here is that ft2x is ft2 times the cosine of the angle theta 2. And it may seem like it's an issue that I don't know ft1 or ft2, but I do know theta 1 and I do know theta 2. And so I can begin to plug in now and get something out of this. Because I write ft1 and then theta 1 was 30. So I can write ft1 times the cosine of 30 degrees, and that's equal to ft2, which I have no idea what that is, times cosine theta 2, and the cosine of theta 2 is going to be the cosine of 60 degrees, because theta 2 is 60 degrees. And this doesn't really seem like it gets you anywhere, but it does. Because if we go ahead and let's just say, for no reason at all, just because, you just pick one, let's just go ahead and solve this for ft2. If I solve this for ft2, I get ft1 times the cosine of 30 degrees over the cosine of 60 degrees. And the cosine of 30 is something like 0.866, and the cosine of 60 is a half. And so when you take those and you divide them, it's important to realize now what we've done is we've solved for one in terms of the other, one tension in terms of the other. If you take cosine of 30 divided by cosine of 60, you get approximately 1.73. And so we can say that FT2 is about 1.73 times FT1. And if you take these things to 2 or 3 digits, really that's all you need, particularly because the weight is only given to 2 sig figs, and so we're not going to go too nuts. And that's it for the x direction. The bulk of the work now comes with the y direction equation. And so for the y direction equation, if you remember, I'm just going to pop back here, we had Ft1y plus Ft2y, the upward forces, minus Fg, the downward force. And in a very similar way to what I did over here with the x direction equation, we can substitute in the equations for the components of these vectors. I'm going to do 2 things at once here, so listen very carefully. I'm going to sub in for Ft1y and Ft2y, and I'm going to get the weight to the other side of the equation. And so what I'll have here then is Ft1 times the sine of theta 1 plus Ft2 times the sine of theta 2, and that's going to be equal to Fg. And now I can begin to plug in my numbers. I have Ft1 times the sine of 30 degrees plus Ft2 times the sine of 60 degrees, and that's equal to 150 newtons. The sine of 30 is 0.5, and the sine of 60 is 0.866, so I'll write Ft2 times 0.866, and that's equal to 150 newtons. And once again, now I'm stuck, because I have one equation with 2 variables that I don't know. And when you get to here, that's when you bring in the result from your x direction equation. So the x direction equation here says Ft2 is 1.73 times Ft1. So what I have then is I got a half of Ft1 plus 0.866 of Ft2, but Ft2 is 1.73 times Ft1, and that's all equal to 150 newtons. And now all you have to do is multiply these numbers. So I have 0.5 times Ft1 plus, and if you take 0.66 times 1.73, you get about 1.498 Ft1. And that's equal to 150 newtons. And notice now we have like terms on the left-hand side. We have 0.5 Ft1 plus 1.498 Ft1. And notice there the math is actually super simple to work out. That ends up being 1.998 times Ft1. And that's equal to 150 newtons. And so, of course, when you divide both sides by 1.998, you get that Ft1 is equal to 75.1 newtons, or to 2 sig figs, because that 150 is given to 2 sig figs, 75 newtons. And the important thing to realize here is that the instant you solve this for Ft1, you now have Ft2. Because we know the relationship between Ft1 and Ft2. And so that's really our last step, and unfortunately I'm going to have to show this on another slide here, but we know that Ft2 is 1.73. Ft2 is 1.73 times Ft1. And we just calculated here that Ft1 is 75 newtons. And so when we do that math, 1.73 times 75 newtons, we get that Ft2 is equal to 129.75 newtons, which, to 2 significant figures, is 130 newtons. And that's it. That's how you solve one of these statics problems. In review, it's a long one, but in review here, quickly. First, you draw the free body diagram. If there's any of these straight ropes, you got to just use the diagram to recognize that means the tension in that rope has got to be equal to the weight. Then you write your x and y equations. Draw a component diagram if it helps you. The sum of the forces in the x direction is 0, so in an orientation like this, that means the tensions in the x direction have to be equal. In the y direction, some of the forces in the y direction are equal, so that means all of the y components going up have to be canceled out by the weight. And so we have the ft1y plus ft2y minus fg equals 0. Next, you use your x direction equation, plugging in the angles for the components to solve for one tension in terms of the other. Doesn't really matter which one you do, you get the same answer either way. Then with the y direction, you substitute in your equations for the components, and then you substitute in the result of your x direction equation. Notice, once we got all the way down here, we substituted in that ft2 was 1.73 times ft1. And once you have that substitution made, now there's one equation, and the only unknown was ft1. And so doing that math and putting it all together allows you to just combine like terms and solve for ft1, which is 75 newtons. And once you have ft1, because you already know the relationship between ft1 and ft2, you just go ahead and solve the thing for ft2. It's always going to be like that. And the last point we want to make here about this problem before we move on to another one is to go back to the original diagram here. And actually, I'd like to erase everything that I drew on top of this diagram to just draw the results of our work here, which is that this cable had a tension of 130 newtons, whereas this cable had a tension of 75 newtons. And that answer makes a ton of sense, like a ton of sense. And the reason why it makes a ton of sense here is because look at the orientation of the two cables. What do you notice about cable 2, this one, compared with this one? Cable 2 is much more vertical than it is horizontal. And that actually gives you some insight into what the answer should be. When a bird feeder or any object is supported by two ropes, the rope which acts more vertically must have a larger tension because its vertical component has to support more of the weight of the bird feeder. Remember, the weight of the bird feeder is a force which only acts in the vertical direction. And because it only acts in the vertical direction, only components that act in the vertical direction can cancel it out. And so that burden, the burden of supporting the weight of the bird feeder, must be taken on by the rope which acts more vertically than the other. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at another example of these problems. Okay, so to wrap this up for today, I just want to do one more problem where you basically just try this thing on your own. So that problem is on a worksheet attached to this post. But the entire question fits on this slide here, and so I'm just going to display it here. It says in this problem, a ball of mass 0.5 kilograms is suspended by two strings as shown in the diagram at right, that diagram over there. And part A is asking you to determine the weight of the ball. Part B is asking you in the space below to draw and clearly label all of the forces, not just the components. acting on the ball. Or sorry, I just said not just the components, but not components. Remember, as I previously mentioned, components are not supposed to be in a free body diagram. On the AP test, actually, sometimes they explicitly tell you that. Forces only, no components. Either way, it's a good thing to remember. And then they give you the dot here, which I referred to before, that they will give you a dot on the AP test to show you the object. So what I'd like you to do right now, because A is really quick, I'd like you to complete parts A and B, and then we'll go over them. So pause this video here, complete parts A and B, and then we'll go over them. Okay, so part A is asking you to determine the weight of the ball. This part's super easy, right? So we have the mass here is 1/2 kilogram, and we have our value for G, the acceleration due to gravity's magnitude, 9.8 meters per second, and we're looking, meters per second squared, and we're looking for the weight Fg. So Fg is equal to mg, as we've previously reviewed, and so Fg is equal to 0.5 kilograms times 9.8 meters per second squared, and we get the weight of this object, 0.5 times 9.8, is 4.9 newtons. Again, because that mass is only given to one significant figure, let's just leave it as 4.9. If you want to round it to 5, go ahead, but I think it's not safe to assume that them giving the answer here to just one significant figure is on purpose, because they want you to round everything to one sig fig. So let's go ahead and just call that to 2 significant figures. And the second part of the problem says, in the space below, draw and clearly label all the forces, not components. So fairly obvious should be the weight of this object, since we just calculated it, which is going to come straight down. And we'll label that Fg. And then we're going to have the tension in rope 2. Notice it's labeled here as rope 2, so we'll call that Ft2, going up and to the right like this. And then we will draw the first rope and label that Ft1. And since there is no grid space, we're not going to go too nuts about the scale. Having said that, it should be clear to everybody that we can take an opportunity to make a prediction. And we can make a prediction by answering a couple questions. So the prediction here is going to be which one of these tensions is going to be bigger. That's the thing we're trying to predict. And so what I want to ask you is to consider, well, for any force, and that includes the tension, it's going to be the square of the x component plus the square of the y component, and then under the radical. So what we should ask is, how is the x component of Ft1 going to compare to the x component of Ft2? Well, since this object is in equilibrium and the horizontal forces have to cancel out, they're going to have the same size horizontal force. So the x components are going to be the same. So that means whichever rope has a larger y component is going to have a larger overall tension. And looking at the diagram, along with the note that we just wrote before this, whichever rope is more vertical is going to have a larger vertical component and thus a larger tension. So because T1 acts more vertically, it's going to have a larger tension. And so that's why the arrow is a little longer. All right, I'd like you to pause this video here now and do part C. Essentially what you're doing is you're following along the procedure from the previous problem. But I'd like you to pause this video here and take a couple minutes to answer part C. And when you hit play, we'll go over it. Okay, so your calculation for this problem should look a little something like this. So as we saw in the text of the problem, we know that the weight of this object, well, we calculated that from part A, is 4.9 newtons. We also know that theta 1 is 53 degrees. And we also know that theta 2 is 37 degrees. It should be noted here that the angles in this problem do add up to 90, and the angles in the other problem did add up to 90. That is a coincidence. It is not always like that. And here we're looking for FT1 and FT2. And I just want to address that for 1 second. Some of you may have realized throughout the course of this that you can actually use like a super shortcut here to do the Pythagorean theorem to answer these questions, because the angles add up to 90 degrees. But I think that is a terrible idea to rely on that, because if the angles don't add up to 90 degrees, then you're in trouble, because then you won't know how to do them. So using the proper procedure here and learning how to do that is going to be crucial. Okay, so as you saw from the last one here, the first move we got to make is we have to write our equation for the sum of the forces in the x direction. And I'd like to keep this on one slide, so I'm going to do this here. So the sum of the forces in the x direction, as we know, has to be 0. And so that's going to give us the force going to the right, which is going to be ft2x, minus the force going to the left, ft1x, and that's going to be equal to 0. So that means that ft2x equals ft1x. And because we know the equations for the components, that means ft2x is going to be ft2 times the cosine of theta 2, and ft1 is going to be, or excuse me, ft1x is going to be ft1 times the cosine of theta 1. And that's it. Now, if we solve this for ft, I'm going to change it up here and do it the other way, just in case you did it the other way. I'll solve this for ft1. And so we'll say ft1 is going to be ft, well, I should say cosine theta 1, by the way. ft1 is going to be ft2 times cosine theta 2 over cosine theta 1. And so plugging in, we have ft1 equals ft2, we don't know that yet, times the cosine of theta 2, which is 37 degrees, over the cosine of theta 1, so the cosine of 53 degrees. And when you do that math, the cosine of 37 over the cosine of 53, we get that ft1 is 1.33 times ft2. And if you chose to solve it for ft2 instead, then what you should have is that ft2 equals like 0.752-ish of ft1. Really, it should be cosine of 53 over the cosine of 37. And so that would give you 0.754, actually, if you don't round first. So that's the idea. Okay, so there's our result from our x equation. And I'm going to leave the room under here for me to come back to that at the end, once I get my result from the y equation. So the sum of the forces in the y direction is also equal to 0. And that means the forces going up, ft1y plus ft2y, is going to be equal to fg. All the forces going up have to equal all the forces going down. You could say ft1y plus ft2y minus fg equals 0, or you can say this. Writing either of them is totally fine. It does not matter to me. And so now plugging in, we get ft1 times sine theta 1 plus ft2 times sine theta 2 equals fg. And now we plug in our numbers here. We have ft1 times the sine of 53 degrees plus ft2 times the sine of 37 degrees is equal to 4.9 newtons. And so that means that Ft1 times 0.799 plus Ft2 times the sine of 37, which is 0.602, is going to be equal to 4.9 newtons. And now I'm going to plug this result in. Ft1 is 1.33 times Ft2. So I have 1.33 Ft2 times 0.799 plus 0.602 Ft2 equals 4.9 newtons. And 1.33 times 0.799 is 1.06 Ft2. And plus 0.602 Ft2 is going to be equal to 4.9 newtons. And 1.06 plus 0.602 is 1.662 Ft2, right? Because these are like terms, we can combine them. And that's equal to 4.9 newtons. And when you do that division, 4.9 over 1.662, we get Ft2 equal to 2.95 newtons. Cool. Okay, and so now just moving on back to the first part. Last, and I'm only organizing this like this because it's hard to fit this all onto one slide here. We know that Ft1 is 1.33 times Ft2. And so that means Ft1 is 1.33 times 2.95 newtons. That means Ft1 is equal to 3.92 newtons. And that's it for part C. We have our two tensions, and we're in business. And notice, for those of you who are banking on the shortcut here, if we take 2.95 and we square it, and we add to that 3.92 squared, we get 24.0689. And when we take the square root of that, we get 4.906, which, setting aside rounding errors, is our weight. The Pythagorean theorem is an interesting little shortcut for this one. And so that's it for part C. And that brings us to part D and E. And that's where we are going to leave this for today. Parts D and E are very interesting little conceptual questions. And I really want to get a sense of what it is that you're thinking about these things. So part D says indicate whether T2 is now greater than, equal to, or less than the value reported in part C. Justify your answer qualitatively without using equations or calculations. So if we take this left-hand string, and instead of having it up like this, if there was another wall here, and we attach that to this wall like this, is Ft2 now going to be bigger, equal to, or less than its value that we just calculated, which is a 2.95 newtons? To be clear, you do not have to use equations or calculations to answer this. And in fact, I don't want you to do that at all. Do not recalculate this. What I want you to do is I want you to think about the concepts here. Everything that we've said so far should enable you to come up with the answer. Your submission of this answer is not going to be graded on whether it is right or wrong. I just want to know what you're thinking. So write up an answer, a couple sentences, and submit that along with your answer to part E. Part E says determine the new vertical component of T2 without using equations or calculations. Justify your answer qualitatively. What I'm going to say about this one is one sentence will do the trick. For D, I'd like to see a few sentences. Now, normally, the answer to these questions that I'm posing you in the video are due the next day, because the next day I'm going to go over the answer in the video. But because your next video is not going to be posted until Monday, this is going to be due Monday morning. Tomorrow is the test. Good luck to you all. If you already took the test and are now looking at this over the weekend, I hope it went well. And that is it for today. Take care, everybody.